All right, welcome to our part 3 of our lecture video series from Monday, May 8th. Do want to make a quick note? I had a sign error here. There are two different ways you'll see the Clausius-Clapeyron equation, and it depends on what order you do your temperature difference in. I like to, let's see here, if I have P1, P2, then yeah, I want to keep myself in order, T1, T2. This is actually probably not my favorite way to think about the Clausius-Clapeyron equation, so let's just kind of re-express it in the way that I'm going to use it because I like it this way. So if we do the natural log of P2 over P1, so final over initial, that is going to be, let me see here. Do I have 1 over 2? Sorry, I'm just checking. 1 over 2, 1 minus 2. Yes, okay. P2 over P1 is equal to now positive heat of vaporization over R times 1 over T2 minus 1 over T1. Again, I like this expression a little bit more just because I don't have to worry about dropping this negative sign. This is kind of like how I will now, from this point forward, use the Clausius-Clapeyron equation. And let's use it. So for example, let's see here. The boiling point of water is, of course, not 0, 100 degrees Celsius. If the enthalpy or heat of vaporization of liquid water is 40.7 kilojoules per mole, what is the vapor pressure of water at room temperature, or 25 degrees C? All right, so there are some important pieces of information. Let's just kind of start pulling them out of the problem. So first of all, we are told the boiling point of water is 100 degrees C. So let's remind ourselves about what we know about the boiling point. So at the boiling point, the vapor pressure of any substance is equal to atmospheric pressure. In other words, it's equal to 1 atmosphere. And we know in this case that this occurs at 100 degrees C. However, looking back at our gas constant in the Clausius-Clapeyron equation, we need to make sure that our temperature is in Kelvin. So we are going to need to add 273.15 to 100 degrees C. So that's 100 degrees C plus 273.15 Kelvin. That equals 373.15 Kelvin. All right, what else are we given? We are told that the enthalpy of vaporization of water, so we know the heat of vaporization of water, this is 40.7 kilojoules per mole. And let's check our unit of our gas constant. This wants us in joules, so we need to ensure that this is put into kilojoules, or sorry, out of kilojoules into joules. So I'm going to multiply this by 1,000. or keep it as 4.07 times 10 to the, I believe that's 4 joules per mole. Okay, now let's check. One, two, three, four. Yep. Yay. Okay. All right. So again, we're just kind of pulling information out of the problem. Now we have, what is the vapor pressure of water at room temp? So we know that we're looking for the vapor pressure of water at 25 degrees C. Or let's call this our new temperature T2, which is 273.15 plus 25. This gives us 298.15 Kelvin. All right, again, this is our goal. This is what we want to find, this vapor pressure. So let's call this P2, and let's call the other one P1. So if I'm going to use my Clausius-Clapeyron equation, that is the natural log of P2. So this is what I don't know. This is the vapor pressure of water at 25 degrees C over P1. That is going to be the vapor pressure of water at some initial temperature. So here we have room temp. Here we have our boiling point. And we know by definition of the boiling point that our vapor pressure is 1.00 atmospheres. That is equal to the heat of vaporization, so the enthalpy of vaporization of water in joules per mole, 4.07 times 10 to the 4 joules per mole, over our gas constant, which has been re-expressed so that it's in new units to accommodate this energy unit. That is 8.314 joules per mole Kelvin. So far we have taken care of the natural log of the fraction of our vapor pressures or proportion of vapor pressures. That's equal to the heat of vaporization over R times now 1 over T2. So the final temperature is our room temperature, right? This is our 298.15 Kelvin minus 1 over our starting temperature, or the temperature at which we have a vapor pressure of 1 atmosphere. That is 373.15 Kelvin. All right, let's see if we can't do some of this grody math, because it is indeed grody. So let's start, the way that I like to do this is I like to start by looking at what's inside these parentheses here. So let's tackle what's going on in terms of these big old grody fractions. So I've got 1 over 298.15 Kelvin. So this gives me 3.35, carrying that 4-digit, times 10 to the negative 3, and this is inverse Kelvin, minus 1 over 373.15. This gives me 2.67, carrying that 98 times 10 to the 3, negative 3, inverse Kelvin. All right, I've now tackled those fractions. Let's move on to tackling this division here. So that is 4.07 times 10 to the 4 divided by our gas constant, 8.314. This gives me 4.89535 times 10 to the 3. And let's check our units here. Joules over joules, per mole over per mole. So I have 1 over per Kelvin, or 1 over Kelvin, which is just Kelvin. Okay, this is equal to the natural log of P vape. And you know what? That P vape is over 1, right? Like, I am lazy. We're chemists. Anything over 1 is itself, so why carry that 1 through? All right, let's keep going, tackling this mighty beast. So I have what this constant is out front. Now let's get what this difference is. So let's see here. 3, 3, 5, 4. And 2, 6, 7, 9, 8. I get 6.74 carrying a 2 times 10 to the negative 1, 2, 3, 4 inverse Kelvin. Please tell me if this math is not what you agree with. I would love to be corrected. Okay, multiplying this out by that constant, that is going to be times 4.89535 times 10 to the 3. So times that. Okay, I get 3.30044. And let's think about what our units are here. So we had Kelvin and inverse Kelvin. Nice, those cancel out. This gives us the natural log of our vapor pressure. And again, since, you know what, I'm actually going to keep that 1 atmosphere just so that we can keep track of our units. I just don't want units to go disappearing on us. Okay. Now we have to apply some algebra because our variable, our x, our unknown, is wrapped up or trapped up inside this natural log function. So the only way to undo a natural log is to apply an exponential, because again, natural log and base e exponential functions are inverses of one another, just like log base 10 and 10 to the functions are inverses of one another. So if I do e to the natural log of vapor pressure over 1.00 atmosphere, if I do that to one side, I have to do it to both. That's equal to e to the 3.30044. And remember, the whole point of doing this e to the natural log, it will cancel out the natural log, thus freeing or unwrapping what was inside. So we now have that vapor pressure over 1.00 atmospheres is equal to e raised to the 3.30044. So this is not EE, this is literal Euler's number, base E. So E raised to the, so 3.3004 as an exponent, so E raised to that, this gives me 2.718. Okay, let's see if this makes some sense, because I don't think it does, which means we made a math error somewhere. Love this. Okay, cool. So if I were to multiply over my vapor pressure in the denominator, this would become 2.718 times 1.00 atmospheres. This brings in that pressure unit. Gives me 2.718 atmospheres. Now let's check if this makes sense. At my boiling temperature, we said this was 1 atmosphere, right? Let's see here. Did I do 2 minus 1? Yes. So why is it that I'm getting a harder or a higher vapor pressure at a lower temperature? So P2 What am I doing here? Oh, I see. Man, this function. Clausius Clapeyron. Beautiful name, but you messed me up. All right, let's fix some mistakes in the Clausius Clapeyron. So 1 over 2, and then 1 minus 2. There we go. No, I lied. This is not the version I want to use because this version is wrong.